Hi everyone. Today I'm going to be talking about a project I'm working on with Michelle Cooke, Scott Marshall, and Jack Loveless, where we're using focal mechanisms to delineate between alternative, active, subsurface fault configurations of the southern San Andreas Fault at the San Gorgonio Pass. The activity of the northern pathway of the restraining bend at the San Gorgonio Pass is still a topic of debate. We want to know if this northern pathway is active today because restraining bends are thought to be structural barriers to earthquake rupture propagation, and being closer to knowing if there are one or two active pathways in this region can be beneficial for earthquake rupture modelers and to understanding the seismic hazard of the area. So today we're going to focus on delineating between two geometries, and the first one is the active Mill Creek model, where the red faults in this map are active, and then the second model is the inactive Mill Creek model, where the red faults are inactive. The way we're approaching this problem is using numerical models, and specifically forward boundary element method models. And so the way this works is a two-step approach. And in the first type of model, they're called steady state, and what we do is load far-field patches along a horizontal basal crack. And then within the model, our faults are able to slip in response to that loading. And what this does is it simulates multiple earthquake cycles, and then we can get fault slip rates along any fault from these models. The second model type is interseismic. And so what we do there is we take these steady state fault slip rates and prescribe them below a prescribed locking depth. And then we have a locking depth transition zone, which is about 3 kilometers wide. And that's where we apply half of the steady state slip rate. And then above that transition zone, the faults are locked. And so from these interseismic models, we can grab surface velocities and stress states at GPS locations and focal mechanism locations. And so in order to delineate between these two model configurations that we've proposed, we can use geologic, geodetic, and seismic data. And so what I'm going to do is start with the geologic slip rates and then work through the other data sets today. So Beyer et al. 2018 conducted a study where they tested 6 plausible geometries for this same region. And what they found was that there were 2 geometries that better matched the geologic slip rate observations than the other 4. But what they could not do is delineate between these 2 configurations. And the 2 models that they determined were the best fitting models are the same as what we're calling the active and inactive Mill Creek models. So we're not going to focus on slip rates today, but if you would like to hear more information about model slip rates and the kinematic compatibility of fault geometries in the San Gorgonio Pass region, I encourage you to check out Jen Hatch's, formerly Beyer, talk at 3 p.m. on April 23rd. In this study, like I said, we're not going to focus a lot on the slip rates, but we do have a plethora of geodetic and seismic data that we can also use to delineate between models. So if we look at the horizontal surface velocities, we can see that our model results match reasonably well to the observed geodetic data. What we also see is that our inactive and active models produce surface velocities that are very similar to one another. And they are so similar, in fact, that we cannot use surface velocities to differentiate between the models. What we can do with this information, though, is take the root mean square error of each of the models with a different prescribed locking depth from 10 kilometers to 25 kilometers and determine which locking depths minimize that error. So in this case, the 12.5 and 15 kilometer locking depths minimize the root mean square error, and we will use those locking depths throughout the rest of this talk. While the surface velocities themselves cannot differentiate between the models, what we can do is look at the strain rate maps. And so what we do here is we invert the surface velocities for strain rate, and then here on the right, I'm showing the maximum contraction rates, and the middle and bottom plot are actually the difference between the observed maximum contraction rates and the models. So at the top, you may notice the dark purple regions are where there's more contraction, and that is localized within the restraining band. And then those yellow-orange areas outside of the restraining band are regions of less contraction. So if we look at the difference between the observed and then the inactive and active models, we can see that the active Mill Creek model produces contraction rates within the restraining band that are similar to the observation. But the inactive model fits the contraction rates outside of the restraining band better than the active model. So what we do here is take the total misfit for our focus area, and we see that the inactive Mill Creek model has a lower misfit of 28% than the active model, which has a misfit of 39%. But we really want more information to determine a best fitting configuration. So now we're going to turn to the seismic data and specifically look at focal mechanisms. Before we can get to the model results, we needed to do a completeness analysis and decluster our focal mechanism catalog. So we started by only selecting the A, B, and C quality events, and that gave us a maximum rake uncertainty of 45 degrees. And in terms of slip sense, this uncertainty is 0.5, and that will come up in the next few slides. The next thing we needed to do was a completeness analysis. And so what we wanted to do was find the completeness limit and then remove any events below that completeness limit. So an example of how we did this is shown on the top left plot, where we plotted the number of events or the frequency of a certain magnitude, and then that red dashed line is where we determine the magnitude of completeness, and any event below that red dashed line was removed from our catalog. After we did our completeness analysis, we decided to decluster the catalog, and what this does is it removes any really tiny aftershocks from small earthquakes, so we're really just capturing the inner seismic stress state. And in order to decluster, we utilized the threshold from Zaliapan and Benzion 2013 that they determined based on the event's distance from a specific cluster center and then the event magnitude. And so overall, our final focal mechanism catalog had 5,345 events, with average slip senses generally being strike slip. So once we have our focal mechanism catalog, we can start to compare our model results to one another and then to the observation. So on the right, you're seeing maps where the opaque circles are 477 locations that the model predicted slip senses differ by more than 0.5. And that 0.5 is the maximum slip sense uncertainty for the observed catalog. So these 477 locations where the two models differ by more than that uncertainty have the potential to delineate between the models. So in order to determine which model better fits the observations, we looked at the frequency of slip sense for the locations where the models differ. And that's what's plotted in the inset top right of each map. And the first thing that we note is that the inactive Mill Creek model slip distribution, or slip sense distribution, better matches the observed catalog than the active Mill Creek model. And the active Mill Creek model just produces way more reverse slip sense events than the inactive model or the observed catalog. We also just wanted to know if we're seeing a bias for the spatial clustering of where the models differ. So we're going to look at volume averages for the events where the models differ. So here we're comparing the volume average slip sense maps, and we can see that the active Mill Creek model definitely has a larger area of reverse slip sense than both the inactive Mill Creek model and the observed catalog. If we then take the misfit for each of these models, we can see that the inactive Mill Creek model has a lower misfit of 36% than the active Mill Creek model, which has a misfit of 57%. So we're definitely seeing in both the individual locations and the volume averaged maps that the inactive Mill Creek model better fits the observed data. Looking at the cross-sections of model slip sense, we can see 3 areas where the models really differ. And so these 3 areas are denoted by the opaque ellipses, and then the points within the ellipses are indicating the focal mechanism locations where the models predicted slip senses that differed by 0.5. If these points are colored gray, then that model's prediction of slip sense matched the observation, but if these points are colored black, then the model's prediction did not match the observation. The first thing we want to note is that more of the points within the inactive model match the observation than within the active model. And this is because within the active Mill Creek slip sense cross-section, what we notice is that there is more reverse slip sense area. And if we look at the dip slip rates for the San Gorgonio pass thrust, which is labeled SGPT in the slide, we might be able to understand why these 2 cross sections differ where they do. Looking at the dip slip rate of the San Gorgonio pass thrust, we would expect there to be a zone of localized contraction above the locking depth of a semi-infinite slipping fault. And because the models produce different slip rates, we would expect these zones of localized contraction to differ in size. So the first thing I want to point out is that these zones of localized contraction would favor reverse slip sense. So with the active Mill Creek model having a higher dip slip rate than the inactive Mill Creek model, we might expect this zone of localized contraction to be larger. And in the slip sense cross sections, this is what we saw, especially in the footwall of the San Gorgonio pass thrust. To wrap things up, today we've shown forward numerical model results compared to geologic, geodetic, and seismic data. The slip rate and horizontal surface velocity comparisons could not delineate between the active and inactive Mill Creek models. However, focal mechanisms and strain rates inverted from surface velocities do have the potential to delineate between active subsurface fault geometries of the southern San Andreas fault at San Gorgonio Pass. Both the strain rate and focal mechanism comparison results show that the inactive Mill Creek model produces maximum contraction rates and slip senses at focal mechanism locations that better match observations than the active Mill Creek model. If you have any questions or comments, please feel free to contact me. And thank you so much for listening.